Hey guys, can you hear me? All right. Okay, have you guys tried the demo site yet? I know some of you have already done that, but all right. So we have a week before our test. I'm assuming majority of everybody in our class has some other test before that. I'm at least hoping that you have some experience with the site, not only with the demo site. Like, you're going to have to do the demo site for me, but I want to see how this goes with everybody else's classes too. Okay, so everybody knows that, like, you have multiple ways to upload. If you're going to do a picture, okay, so what I did is I took a picture of my work, or I just took a picture with my phone, and then I airdropped it to my computer, and then I had to convert the file to a JPEG, and then I could upload it. And when you do that, like, all the pictures that you take, you're gonna upload one at a time, and then you're gonna make sure you uploaded all of them, and then you hit submit. Okay, did anybody have any issues with the demo site? Okay. So what I want to do is I want to go over the optional FRQ that I posted. I'm going to go over that, and then if you have any other questions, we can go over those. But I thought this was a decent FRQ. I thought it was worth looking at because it has some mechanism questions in there too. And I don't know if any of the other FRQs I gave you guys had anything to do with mechanisms. So I'm going to go over that. If you want, you can go ahead and grab like, if you wanted to print it out, you could really quick. Now, what you have to upload this week. So this FRQ is completely optional, okay? But the other FRQs, you have to upload those. I am making the video part of that this week optional because I'm not going to upload it until probably either tomorrow or Friday. But I'm not gonna count that like that. The upload will be counted as a grade, and I'm gonna look at those answers, but I'm not going to look at the video. So make sure you do the FRQs. Make sure you go back and you actually grade the FRQs, and then you also need to do the demo site. You have to do that. All right, so let's go ahead and look at this FRQ. Okay, so right here it has a potential energy diagram. So when you're looking at this, every time that you see a hump, that represents a step. So this particular reaction has 2 steps. So what'll end up happening is you're starting with the reactants. The reactants have so much potential energy. You're going to give it energy. So this is the activation energy. We get to the top of the hump, and this is where we are forming new bonds. We're breaking old bonds. That's called the transition state. And then we go down to the products of that first step. So right here, okay, that is when we have an intermediate. An intermediate is going to be something that we produce in one step and then we use it in the next step. So now that those things have so much energy, We have to apply more energy for the activation energy of that step, and then we go down to the products. So right here it tells you the reaction mechanism below is listed. So here's our reaction, and then here are the steps. So we have step 1 and step 2, right? The overall equation. So all you're doing for that, you're just putting them together. Anything that's on both sides cancels. So we have H2, that's on both sides, so that stays as a reactant. We have ICl, but we also have ICl down here. So we have 2 of those. Okay, and then HI, well, it's here and here, so that gets canceled. Okay, this is an intermediate. I produce it in one step, I use it in another step, so that's an intermediate. A catalyst is going to be something that's included as a reactant and then is spit back out as a product. So an intermediate is going to be something that's produced in one step and then used in another step. All right, so now we have HCl. Again, there's 2 of those, and they're on the same side, so it's just additive. And then I2 does not cancel. So this is the overall equation, okay? So all you're doing is you're just putting those together. Okay, so based on the reaction profile, identify the slow step. Well, if you look, here's the first step, here's the second step. The first step requires more energy. So that step should take longer because it requires more energy to be put in initially. So based on this profile, the first step is going to be the slow step here. All right, and then the next question is asking for the rate law. So based on this, what is the rate law? Well, the rate law is going to be based on the slow step. And we just decided that the first step is the first step, or the slow step. So the reactants of the slow step will give you the rate law. So rate is equal to little k multiplied by H2 to the first and ICl to the first, because it's based on the stoichiometry of the slow step. Now, it would be different if the second step was the slow step. Then I would have to account for the fact that it shows up in a step before it. But this is the slow step, so it's based on the stoichiometry of that. It's never going to be based on the overall reaction. Okay, so when you look at the mechanism, the slow step gives us the rate law. Okay, so then determine the sign of the enthalpy for steps 1 and step 2. So when I look at this, well, overall, this reaction should be exothermic because my reactants are up here, my products are down here. My products have less energy than my reactants. So that means that energy has to be released. So, but if you're looking at each individual step, you have to compare the reactants to the products of that step. So it's the same thing here. I have more energy in my reactants, so that's going to be exothermic. And then here's my second step, reactants to products. I have less energy here, so it's also going to be exothermic. So both of them, the delta H should be negative. It's not asking for the value, it's just asking for the sign. Okay, so you have a question. Hold on. Okay, so if the slow step was step 2, it would actually be one of those weird occasions where the ICl is to the half. That really, it's rare to see that on the AP exam anymore, but that does it happen? Yes, it does. So if step 2 was the slow step, oh yeah, and then also if step 2 was the slow step, we can't have intermediates in the rate law either. So I would have to go back. Oh, so hold on. Okay, let's just go ahead and go with this scenario. So let's say that this was the slow step. So rate is equal to little k HI to the first, ICl to the first, if I'm just basing it on that. But I have to double check because this is a step 2, and I forgot that there was an intermediate in this one. Okay, if we have an intermediate, you can't include the intermediates in the rate law. So this has to be replaced with the reactants that create that. So it would be little k H2 to the first, and then ICl, but we already have ICl in here, and that's what I forgot about. ICl is going to be to the second, not to the half. That would be a different situation, but you can get a fractional power here. Let's see. Yes, so if you are given the potential energy diagram, the one that has the highest amount of activation energy should be the slowest because it takes longer to get to that minimum amount of energy. So if you know that the activation energy is going to be high, it's going to be a slower step. Now remember, even if you have something that has a high activation energy, and it maybe does go slower, it does not mean that it's thermodynamically unfavorable. It can still happen. It just takes a bit more time and a bit more energy to get there. All right. Okay, so let's look at D. Oh, wait, we already did that. Okay, so the enthalpy for all of the steps is negative, and then overall it's also going to be negative. Okay, so the next one is asking about intermolecular forces. Okay, so we have boiling points. So we have to identify the intermolecular forces in I2 and ICl. Well, I2 is just I bonding to itself, so I2 is nonpolar. So the only thing that I2 is capable of is LDF. And remember, LDF, London dispersion forces, is when you have molecule, the electrons can move around in the molecule and create temporary dipoles. So they create a temporary negative region and a temporary positive region. All molecules are capable of LDF. It's just if it's nonpolar, it can only do LDF. And then if I look at ICl, well, ICl is also capable of LDF, but it's polar. I with a Cl, we're going to have a polar bond, so that means that it's also capable of dipole-dipole. Now, this question is asking how come I2 is higher than ICl? Okay, so if I look, I2 is only capable of LDF. This one is polar, it's capable of dipole-dipole. This one should have the higher boiling point, but that's not what we're actually seeing. So it's asking you to explain that discrepancy. Well, if this has a higher boiling point, this means that I2 has stronger IMFs. Okay, so that's part of it. But why does it have stronger IMFs? It's because it has more polarizable electrons. I have more electrons that are able to move around and create those temporary dipoles. So that's the reason behind that. So if you see something like this where it's asking you to explain that discrepancy, well, that's because if you have more electrons in the molecule, you can create more temporary dipoles, which makes the traction of the molecules to each other stronger. All right, so the next one, identify the intermolecular forces in HI and HCl. Explain why the boiling point of HI is higher than HCl. This is a pretty similar question. It's just the only difference is HI and HCl are both polar molecules. So since they're both polar molecules, they're capable of the same things, LDF, dipole-dipole, for both of them. Make sure, if it's a comparison question, make sure that you mention both molecules. And then let me just finish this one question. And then why is HI higher than HCl? Well, the reason that it's going to be higher is because HI, it's the same reason. HI has stronger intermolecular forces because it has more polarizable electrons. So if you go and you look at the mass, I is much, much higher than Cl, so it means it has more electrons. Okay, so let's look at the chat. Dipole-induced dipole. Okay, so if we had dipole-induced dipole, that would have to be, okay, so in order for it to be dipole-induced dipole, that means that you have to have two different items. So it can't be HCl interacting with another HCl molecule. It can't be HI interacting with another HI. Dipole-induced dipole means that you have something that's polar, okay? You have a polar molecule and a non-polar molecule, and then that would be the reason they're attracted to each other. So it would be like ammonia attracting I2. So if I have like NH3 and I have I2, well, this is non-polar, and then this is definitely polar. So what ends up happening here is this polar molecule, because it's got that permanent dipole, it's able to attract the electrons and the I2 to move over. It induces a dipole. So it would have to be a polar molecule with a non-polar molecule. That would be the only reason they would attract each other, because that dipole over here induces a dipole on this side. Yeah, no problem. Another good point would be, like, you could also potentially see like ion with dipole. Now, if it's like an ion dipole, that would be like a water molecule interacting with something that's ionic. So pulling the ions apart in a solution when it's going through that dissolving phase. Okay, so the next one is a KP question. So HI is formed by this reaction at 450 degrees Celsius. The KP is 50. So what's the KP? Write the KP expression. So again, for KP, do not put brackets. Make sure you're referring to the partial pressures. So the partial pressure of HI squared over the partial pressure of H2 to the first over partial pressure of I2 to the first. Okay, so make sure there are no brackets. So if it's Kc, you're going to use brackets. If it's Kp, you're going to use partial pressure. All right, so we have a container, 1 liter. It's got a pressure of 1 and 1 for the reactants. Calculate the final pressure of HI. So it doesn't tell us anything about the total pressure for this, so I can't use Dalton's law here, but I can definitely set up an ice table and do that. So that's what I'm going to do. I'm going to set up an ice table because I need the equilibrium amount of the HI. So initially, it tells me that it's at 1 for both of these, and this is just pressure. We're using Kp, so it's got to be pressure. Product should be 0. We'll change that. I should subtract some number. And then here I'm going to add 2x. Don't forget that. This should be 1 minus x. This should be 1 minus x. And then this is going to be 2x. Well, I know what the Kp value is. It's 50. So I can plug that into the Kp expression with here and then solve for x. So that's what I'm going to do. So Kp is 50 here. Partial pressure of HI squared, that's the whole thing, that's the 2 also, divided by 1 minus x, 1 minus x. Now, normally we would use approximation here. You can't do that because Kp is pretty large. It's larger than 1. K has to be less than like 0.001 at least. So that's not the case here. So we are going to have to use quadratic, but this one actually ends up being pretty simple for the math. So 50 is equal to 4x squared. You have to square the 2, okay? Divided by, okay, 1 time, just go ahead and expand it all out. So 1 times 1. One day I'm going to back up. 1 times 1 is 1. 1 times negative 1, x, so minus x. Then do the other side, so minus x times 1, so that's another negative x. Negative x times negative x. Okay, so now I'm going to erase all this. Okay, so now multiply both sides by this equation. So 50 times this, and minus x, that's 2x. That's equal to 4x. All right, so now we're gonna get 50 minus 100x plus 50x squared. All right, now remember what we're trying to do is we're trying to get it into that quadratic format. So basically just subtract 4x on both sides. So we get 50 minus 100x plus 46x squared, and that's equal to 0. Okay, so now you take out your calculator, and then all you're gonna do is you're gonna go to apps, go to the Polysmelt, however that's spelled, I don't remember, but it's under apps. Guys, be familiar with your calculator just in case. Could they ask something like this? Yes. Would they probably expect you to solve it with a quadratic? No, I would actually expect you to have more, have the total pressure more than anything. Like the total pressure at equilibrium. So you go to this, you hit enter, enter again, and then go to Polyroot Finder. And then you're just gonna hit enter. Everything should be set up. You should have two, you should have real numbers only, decimals, normal, float, degree, and then you're gonna hit next, and then you're gonna hit 46 for the x squared part, negative 100 for b. It really depends on like how your calculator is set up as to which one is which, and then this one is c. And then once you plug that in and you hit solve, you're gonna have two numbers, one of which will not make any sense. So you have 1.3 as an option and then 0.779. Well, if you go back to your ICE table, okay, so if you remember, on your ICE table, you have H2, you have I2, and then you have this. Okay, so when you're looking at this, this is 1, this is 1, this was 0, this was minus x, or plus 2x. So really it has to make sense in the context of this. So 1 minus 1.3 would give me a negative number. That's not going to happen. So it has to be 0.779. So x is going to be equal to 0.779 or 0.8. So at equilibrium, this should be 0.2. 1 minus 0.8 would also be about 0.2. And then 2 times 0.778. That's going to give me 1.6, roughly. Okay, so that was the answer. That was asking for the pressure at equilibrium for the HI. Okay, the next question, if we go down, is asking about the number of moles of I2 left. So I'm not going to erase this just yet because we kind of need that. So how many moles of I2 remain after the reaction has come to equilibrium? Okay, so remember, anytime that you have pressure, the pressure is a result of the collisions against the container. So the more molecules you have, the more pressure you have. So if it's asking about the I2 specifically, well, we have the pressure of the I2 at equilibrium. Okay, so I know how much pressure is being exerted. Okay, I also know, because this is gas, I have a temperature. It tells me it's a 1 liter container. I have a pressure, so automatically your head should go to ideal gas law. It's asking for the number of moles for that one, so it's asking for N. So if your pressure is 0.2, your volume is 1, N is going to be what you're looking for, And then your temperature, it's 450 degrees Celsius. That's actually 723 in Kelvin. So once you solve for the number of moles, you're going to get 0.033. And this is why I think that they're going to have something. I'm really going to hate it if I'm wrong, but I really feel like they'll have something with KP, because then they can do so many different things with pressure. They can go a lot of different areas. Okay, any questions about that, or are we good on that one? Okay, so have you guys have you looked at the other FRQs yet? Because I picked those because I was trying to hit a little bit of everything before we take the test. Okay, can you guys do me a favor? Can you write, well, actually maybe I'll do a poll in Schoology too. I do want to have a few conferences next week, just in case there are last minute questions, or there's something that I think I can maybe quickly go over before your test, but I want to make sure it's not interfering with any of your other APs. So like right now, I know you guys have APUSH. What other APs are we taking? I'll do a poll on Schoology, but just give me an idea. Because I think I'm probably gonna change the schedule for next week, because our AP test is next week. Calc, okay. I don't know, how do you guys feel about the test right now? How do you feel about any of your tests? Yeah, okay. My suggestion about the time is go ahead. First of all, go ahead. I haven't given you guys any of the 2019 FRQs. Pull those FRQs and like literally take one of the longer FRQs and time yourself. Like really, like, because if I were in class, this is what I'd be making you do. I'd be standing over you and telling you to do it, and then you'd have a time. So I know it's like rough, because it's rough to motivate when you're at home, but that's one of the things that I do advise you guys do. Go ahead, pull the 2019 FRQs and time yourself. So a long FRQ should take you roughly 20 minutes. A short FRQ should take you 7 to 8 minutes. Now, when they set up those new FRQs, I'm imagining that they're going to still try to keep in that same time, but really don't fall into the trap of like trying to look up things, okay? Because I don't think they're going to ask you anything that's simple enough to just go and look up and get a simple point. Don't fall into that trap. Just write as much as you can, do as much as you can in that time. And then, for the love of all that is holy, because they emphasize this over and over again, make sure you hit submit. Whatever you do, make sure you hit submit. And do you guys know how you're going to try to answer the questions? Are you going to try to take pictures? Are you going to try to do like a document and then copy and paste? Okay. So when you guys do the pictures, do what I said, because like I mean, make sure that you know how to convert it. Make sure you know, like, okay, so if you're going to airdrop it, like with your phone, make sure you convert it. Make sure you have that done. Like, practice it. You can always go back to that demo site and do it as many times as you want. really doubt that they're going to. Could they potentially like do the thing that they normally do where they take off a point for sig figs, but they usually just do one? What I would do is I would do a simple check. When you do your math, just go back to the measurement, whatever measurement they gave you in the prompt, and just match the number of significant figures to that measurement. Just try to do that, and then you should be okay. Molar masses, usually they like to state them in the problems. Use whatever they have. If they state a molar mass, and then if you have to calculate a molar mass, go ahead and calculate it to 2 decimal points, because that seems to be what they do every single time. So that's my suggestion with sig figs. Don't get hung up with it, but I would try, if you're going to do math, do a quick check. Take the measurement, match the answer to the measurement, and then try to keep your molar mass to 2 decimal places. I would do that. Yeah, so if you get stuck on one part, but you know how to do the second part, just say, like, you just start off with a number, or just say, assuming this, and then just do your work. Like, you should still get carryover points. They're not gonna not take off for that all of a sudden. Does anybody have my test first? All right, does anybody have anything else they want me to like talk about, or you have questions about? Okay, just a reminder, I put 3 documents that I think will be helpful on under, I think, either updates or material. I think I put it under updates. One was on lab stuff. There was another on like thermo questions. I mean, like technically you could print out the thermo thing, but like I said, don't fall into the trap of like, you know, using up your time. And then there was another document, I forgot what else I put on there, but like I would go back and look at those for sure. And like I said, I definitely time yourself with practice. Like do a timed FRQ on yourself and see like how far you get. Okay, if you guys don't have any other questions, I'm gonna go ahead and let you go. I'll do another review session on Friday. I'm not sure what I'm going to go over yet. I'll figure out something. No problem. You too.